Okay, today's lesson 8.5 is on function inverses. Now with the do now, we sort of tie together the composition of functions, and we look at two functions here, f of x equals 2x minus 1, and g of x equals x over 2 plus 1/2. Now, when you take f of g of x, here's all the work, you end up with x as a final simplified expression. Now when you take g of f of x, you end up with also x. Now it's not a coincidence that both answers are x. It is actually the first part of the notes that we learned today, that whenever you take the inverse of, when you take the composition of inverse functions, the solution is always x. And there it is. Composition of inverse functions always results in x. Okay, next slide. We're going to go ahead and complete the tables below for each of the functions above it. So we're going to look at the same functions that we did in the do now, 2x minus 1 and x over 2 plus 1/2, and we will evaluate the domain here. In other words, we're going to take all these input values and find a y value associated with it, and then come up with an ordered pair. So as you can see, for the first one we have -1, which when we multiply by 2, we get -2 minus 1 is -3. Our ordered pair is -1, -3. Once you work out all the other ones, you end up with this as your ordered pair. Now over here on this side, when we plug in -3, we end up with -1, right? Because -3/2 plus 1/2 is -2/2, which reduces down to -1. So our ordered pair is -3, -1. Now if we complete the rest of the table, we will notice something very interesting, and that is all of the ordered pairs with this function are basically reversed. The order is reversed with this function, and that is because these two functions are inverse functions. And that leads us to our next set of notes, which is the domain and range of inverse functions are always reversed. Now, a third thing that we learned today is that when you graph inverse functions, it's a special relationship. So if we take a look here and we graph in the graphing calculator our first function, f of x, which was 2x minus 1, and g of x, which was x over 2 plus 1/2, we end up with this over here. Okay? This one down here is 2x minus 1, and this one right here is x over 2 plus 1/2. Now these are actually symmetrical. Now what I mean by that is if I folded this graph along this green dotted line, then one function would lay on top of the other function. And this is always true for inverse functions. And we call this line of symmetry, we call this also the line of reflection. This line is y equals x. A function f of x is said to have an inverse f to the -1 of x. This is not really a power, but instead it's just a name. So we call this f of x, and we call this inverse f of x. And this inverse is always reflected across the line y equals x. Okay, the fourth bit of information that we discussed today is that if you have an equation, a function right here, in the form of an equation, and you are asked to algebraically come up with the inverse of this function, there's a certain process you follow, but the main idea is that you reverse, you just swap the values of x and y. So as you can see, our new equation is x equals 2y minus 1. Instead of y equals 2x minus 1, it's x equals 2y minus 1. And then you solve for y. So the first thing you want to do, which we already did here in blue, is rewrite f of x as y. So f of x becomes y. And therefore, we can swap the x's and the y's. Now we solve for y, so over here for this example, we want to go ahead and add 1 to both sides. That gives us this. Then we divide everything by 2. And we end up with y equals x over 2 plus 1/2. Fourth step is to take your y and rewrite it as the inverse function of whatever you started with. So in this case, it would be f to the negative 1 of x equals x over 2 plus 1/2. Now doing the same steps to g of x, we're going to rewrite g of x with a y, swap the variables. Here's our x and y, so now we have x equals y over 2 plus 1/2. And I'm going to multiply everything by 2 because that will eliminate the fractions down here. The denominators will just cancel out. And we end up with 2x equals y plus 1. One step away, subtract both sides by 1, we end up with y equals 2x minus 1, or f inverse f of x equals 2x plus minus 1, which is actually should be g. There should be a g right here. And if you are observant, you will see that what we started off with, right, 2x minus 1, the inverse is x over 2 plus 1/2, which happens to be the same thing as over here, because like I told you from the very beginning, these two already started off as inverse functions. So when we take this and we invert it, we end up with f of x. This is not a coincidence. This was designed that way. Okay, and now we can go through, we can take a look at these type of regions types questions. The image of a function f of x is found by mapping each point on the function xy to the point yx. This image is a reflection of f of x in what? Well, we know that these are inverse functions because the ordered pair got reversed. So we know that the line of symmetry, the line of reflection, is y equals x. Number 2, we need to reverse each of these ordered pairs. Therefore, the answer is 3. Over here, given the relation A, here are all the ordered pairs. Remember, a relation is a set of ordered pairs. Which statement is true? Both A and inverse A are functions. Now, what is inverse of A? Well, we should go ahead and figure that out. And here it is. Inverse A is basically all these ordered pairs flipped. So here's A and here's inverse A. So, we want to know whether they're functions. And if you remember, functions are determined by whether each x value is unique and there's no repeated values in the x's. So, as you can see, this is true for A. However, with inverse of A, the 2 is repeated. So we have the 2 over here and the 2 over here. This makes it not a function. And therefore, only A is a function. Number 4. Pretty simple, pretty straightforward. We just followed the 4-step process. We swap x's and y's, divide both sides by 2, and our final answer is 1/2 x. Number 5. By what transformation can the set representing the inverse of a function be found? It's a reflection in the line y equals x. Okay, what is the inverse of the function y equals 3x plus 2? You just switch the variables, solve for y, and here we go. You can represent your answer this way. X minus 2 is sharing the denominator 3, or you can write it like this, where x is over 3, or you can show it as the coefficient 1/3 x minus 2/3. Finally, number 7. We have a graph, and we want to express this. We want to basically sketch the inverse of this function. So what I've done over here is I've gone ahead and identified what the ordered pairs are. Here's an ordered pair, here's an ordered pair. There's actually another one over here that I didn't find until later. But this ordered pair is 3, 1. This is 5, 3. So I know the inverse function is 1, 3, 3, 5, which I graphed here and here. So we connect them with a curved line, much like this one, except opposite. So as you can see, this would be the line of symmetry, also known as the line of reflection. And here's your homework. Here's more of the homework. And here are the last 4 questions of the homework. Good luck to you.